Here at IBM Build Labs, we've created some example operators which you can find in our GitHub repo, which we'll show you in a few minutes. In the meantime, I'm going to use those operators to give you a demonstration of some of the typical capabilities that operators provide. I'm also going to show you how to package, distribute and version an operator so that it appears in the OpenShift console of your customers, which hopefully makes it easy for the administrators to potentially discover your solution and also to install and manage that solution going forwards. So the main capabilities of our example operators fall into two categories, either day one or day two capabilities. So day one capabilities are all about that initial task of installing the resources required for the solution. So in our case, our operator installs a simple web application server on the front end and also a database cluster on the back end. Day two is all about automating some of the tasks which might be required to keep the solution up and running. So in our case, our operator automates the task of performing a database backup and also scaling up some of the components. The operator really provides a useful abstraction for the administrator of the OpenShift system. So when you're working with operators, you only need to create very simple resources that actually trigger the operator to create lots and lots of Kubernetes resources behind the scenes. So if your solution consists of lots of different Kubernetes components, or is stateful, or requires various day two activities to keep it up and running, then using an operator could really be the difference between success or failure for your customers. Here in OpenShift you'll find the Operator Hub. It's essentially a catalogue of operators that the administrator of this OpenShift cluster could install. These operators come from the likes of Red Hat, from IBM, and also from independent software vendors as well. And the operators are categorized by their source. So for example, you'll see that many operators come directly from Red Hat, so these are Red Hat software offerings, but there's also a list of certified operators. So these come from independent software vendors who have gone through a process with Red Hat to certify that their operator and their software offering meets certain criteria imposed by Red Hat. There's also a community source of operators as well. So this is an external GitHub repository into which you could put an operator, meaning that it would then become visible via the OpenShift Operator Hub. So that's quite an easy way of publishing an operator. And then finally there's the marketplace. So this is like an app store basically. So if you publish the operator into the Red Hat marketplace, then Red Hat take care of the commercial aspect as well. So you can charge people to use your software which is installed by this operator. Finally, if you don't want to include your operator in any of the sources that I just mentioned, and you'd rather deliver your operator directly to a particular customer of yours, then you can have that customer create private catalogs as well. So that's what I've done for our sample operators. You can see that we have a couple of operators that are only visible within this cluster. Now, whichever approach you decide to take, you have to package up your operator in accordance with a component from Kubernetes, which is called Operator Lifecycle Manager. In a moment, I'm going to install the two sample operators that I just showed you in the Operator Hub, but before I do that, I want to explain briefly how we went about packaging those operators so that they are compatible with the Operator Lifecycle Manager component. So all you need to do is to create a bundle of files, and there are tools to help you create that bundle. In that bundle of files, it essentially describes the operator. So for example, does the operator depend on any other operators to do its work? Also, every operator will define what are called custom resource definitions. So these CRDs are essentially extensions to the standard Kubernetes resources that you might be familiar with, for example, pods or stateful sets. Once you have this bundle of files, then you use again some tools to create a container image containing essentially just those files and put that bundle image into a container registry. Then from that bundle image, you then build a subsequent image which is called an index image, or sometimes known as a catalog image. And what that does is it builds an API around the data or the content of those files. and that API is compatible with Operator Lifecycle Manager. So once you have that catalog image, what you do with it next really depends on whether you want to put your operator into one of those existing catalogs, like the Red Hat Marketplace or the Certified Solutions, in which case you would work directly with Red Hat, or if you're okay with creating a private catalog, as we've done with our samples, then you can take that catalog image and plug it into the Operator Hub on OpenShift. In OpenShift, under the cluster settings, you can actually see the different sources of catalogs which are feeding into the Operator Hub. So here you can see the last two entries here are the custom catalogs which contain our sample operators. And you can see they take their content from one of those catalog images that I was just telling you about, which happen to be located in my container registry. So let's go ahead and install the first of our sample operators, the database operator. As you can see, each operator provides a description of what it does, what it installs, what its capabilities are. When you hit the install button, there's only a couple of questions. Do you want to install this operator in just the current namespace, or do you want to make it available across all namespaces? And what is your policy about installing updates to the operator? Because the provider of this operator could publish updates to their registry. Do you want your cluster to install those updates automatically, or would you prefer to approve them? So let's go ahead and install this operator, which takes just a few moments. Now, just to be clear, this process is installing only the operator. The operator is essentially a pod which contains a controller. It's some logic that we've written in a language called Golang. It's not actually installing a database at all at the moment. It's only installing the operator, which will sit there and wait until the administrator of the cluster creates a resource on the cluster which that operator is waiting to react to. So now that the operator has been installed, we can see it in this list here. And here we can see the different resources, the custom resources that this operator has defined and is sitting and waiting to respond to. Just to explain what these resources mean, the database cluster resource is a definition of essentially deploying an instance of the database in a clustered fashion. So there will be multiple instances of our database. One of them will be the leader, others will be followers, and obviously there are multiple instances for high availability. Database is the definition of a kind of a schema, so that installs some data onto the database. And database backup is another resource that the administrator can create in order to create a backup strategy. So let's go ahead and create one of those custom resources. You can see in this YAML file that the kind of the resource that we're going to create is called database cluster. So that's not a resource that you'll find by default on a Kubernetes cluster. It's a custom resource that was defined by our database operator. And like every resource that you create on Kubernetes, it has some fields or some properties that you can fill in. But the whole point is that this custom resource abstracts a lot of the complexity away from the administrator. So you can see that our resource only has two fields. The first is the image for the container which is going to implement our database. In our case, in our example, we have written our own database server. It's extremely simple, and this is where the database service exists in the registry. And also we can specify how many instances of that database that we want to have for high availability. So let's go ahead and create this resource directly on the cluster. And what should happen is Kubernetes will inform our operator that one of the resources that it monitors has been created, and it's up to the operator now to create the Kubernetes resources that are required to implement a database cluster according to our properties or our criteria. So over on OpenShift, you can see in the custom resource definitions that our database has previously defined the three extensions or custom resource definitions that we talked about. And you can see that under database cluster, there is now an instance of one of these custom resource definitions, which is the one that we just created. Hopefully by now, the operator will have created all of the resources to implement a database cluster. So the database itself is actually deployed as a stateful set that you always find in this namespace. And you can see that it's implemented as a number of pods, and those pods are being created right now. So there's a couple of things you need to know about this sample database. It provides an API, which we're going to be calling from the front-end web application. And also, when we create this database cluster, it initializes itself with some sample data. So first of all, I want to check that the sample data is present. So we can choose any one of these pods which implement our database cluster and go to the terminal for that pod, and then we can call the API to retrieve the data. In this case, it gives back a very simple JSON data structure containing a list of names. So let's move on to look at one of the day 2 capabilities of our database operator. What if you wanted to back up the data that we just saw in the database? You could create a script or have a human periodically execute the steps to back up the data, but potentially that could be error prone. So instead, we can use the operator to automate this task. What we've done is create another custom resource which is called database backup, and the administrator can use this resource to specify their database backup strategy. What the operator is going to do is it's going to create a cron job on the cluster which springs into life on a schedule that has been defined by the administrator to back up the data from the database into a backup repository, for example, Cloud Object Storage. So let's take a look at how you would go about doing that. So let's take a look at how you define that backup strategy. So we do that using the custom resource database backup, and it has 3 main sections. The first is a list of repositories to which you want the database to be backed up to. So in our case, we're defining just one repository, which happens to be Cloud Object Storage on IBM Cloud. And then you can specify either an immediate manual backup or a scheduled backup, which should happen according to the schedule defined here. So in this particular case, obviously, we're requesting both the manual backup immediately and a scheduled backup as well. So let's go ahead and create this resource on the cluster, and we'll see what happens. In response to us creating that database backup custom resource, the operator has created some Kubernetes resources to implement our database backups. So it's created a cron job and a job. The cron job is because we requested a backup that happens on a schedule. So this cron job will launch at the top of every hour, and if you look at its definition, it will use a container image from a registry. That container image executes some code which connects to the database and then uploads the data into Cloud Object Storage. The job is exactly the same, except that it happens immediately because we requested an immediate manual backup. So that gives us an opportunity to look at the logs for that pod and see if it was successful. So here you can see the data has been retrieved from the database. It's the same list of names we saw before. A bucket has been created on Cloud Object Storage and the database backup was successful. In fact, if we go over to IBM Cloud, we can look at the Cloud Object Storage and see that a bucket has been created, and we can actually look at the object inside of that bucket, download it, and verify that the data has indeed been backed up. Let's take a look at one of the other day 2 capabilities of our sample operators, this time auto scaling. Again, the operator uses a cron job to launch a pod on a schedule, and this pod makes scaling decisions. By using our own pod, we can have complete flexibility about what influences a scaling decision. Perhaps it's metrics that come from the front-end application, or maybe from the back-end database, or maybe it's a combination of both. Let's take a look at how it works. The auto-scaling example works to scale up and scale down the front-end web application. So we need to install that now, and of course we have an operator to do that. It's called the application operator, and it defines another custom resource which the operator will react to and deploy a web application server. So let's do that. So here's the custom resource that the application operator responds to. Again, it's pretty straightforward. You can specify the number of pods that you want. You can specify the image which implements the web application server, and you can specify some additional properties like the title and the database name to connect to. So let's go ahead and create that now. As before, back on the OpenShift cluster, we'll see that there is a custom resource definition called application, and we have created an instance of that application. The operator responds to the custom resource by creating a deployment in the application namespace, and the deployment contains just a single pod which implements a web application server. We also have a route which exposes that web application server, and it has a single endpoint called /hello, and if we trigger that endpoint, then you can see that the web application gives us a greeting and also echoes back some of the names that come back from the database. We've set up the web application server to expose a metric which represents how many times that /hello endpoint has been invoked. And that metric can be collected by the Prometheus monitoring software, which is very popular across Kubernetes and is installed by default on OpenShift. So first of all, let's inspect the value of that metric in the Prometheus dashboard. As you can see, at the moment, the /hello endpoint has been triggered 12 times. Let's take a look at the cron job that was created by the application operator. As I mentioned, this cron job is going to execute on a schedule to make the scaling decision. So if we look at its definition, as you'd expect, it specifies a container image to launch to make that decision. The code within that container image is going to connect to the Prometheus monitoring system and query the metric that we just saw for the /hello endpoint. We can either wait for the scaling cron job to execute at the top of the hour, or we can use a command to make it execute immediately, meaning we can check out the results. So if we look at the cron job for the application scaler, we can see now that it has launched a job, the one that we just requested, called manually triggered, and that job launches a pod, and that pod is our custom code which makes the scaling decision. Now, as I said, that gives us complete flexibility to write some code which considers any number of metrics to determine the scaling decision. So let's have a look at the logs for that scaling pod. So as you can see, we have connected that pod to Prometheus, and it has accessed the metric which represents how many times that /hello endpoint was invoked. And you can see that again, it says 12 times. So the logic inside of this pod is actually really simple, and it decides that if that endpoint has been invoked more than 6 times, then the application needs to be scaled up. So how does the application scaler actually perform the scale up? Well, if you remember, we already created a custom resource called application, which the application operator responded to by creating a deployment of exactly 1 pod. Now, if the application scaler pod decides that a scale-up is necessary, it actually locates this custom resource instance on the cluster and edits its definition to specify that actually 3 pods are now required. And you guessed it, it's actually the application operator that gets notified of this change and changes the size of the deployment accordingly. So now you can see that there are 3 pods responding to web application server requests.